Hello, this is your instructor, Tom Porepsky. Let's get back to the third part of Module 5, which deals with something called the binomial probability distribution. If you go back to some of our earlier examples in this module, sometimes we found probabilities by using relative frequencies. Sometimes we basically applied the classical approach, for example, in the roll of one die, where we treat all of the outcomes as equally likely. There are still other cases, what I like to call well-known discrete random variables, where the calculation of the probabilities follows the same format over and over again. And when that happens, we can come up with a rule or a formula for finding the probabilities. One such well-known discrete random variable is the binomial distribution. Let's first talk about the properties of a binomial. The experiment consists of a sequence of n identical trials. And of course, it gets its name binomial from the idea that there are only two outcomes of interest on each trial of the experiment. Let's call them success and failure. It's arbitrary which one we call success and which one we call failure, but just keep it consistent throughout the problem. We're going to let P be the probability of a success. And of course, if P is the probability of a success, then 1 minus P will be the probability of a failure, which we'll have on the next slide, actually. Lastly, the trials are independent. That is, what happens on the first trial does not affect the second, the third, and so on. Going back to the probability of a success denoted by P, we assume that does not change from trial to trial. Now, we still don't have a variable yet, but we're going to define one now. We define a variable x to be the number of successes in the n trials. Notice that x is a discrete random variable. X could be 0 successes, it could be 1, it could be 2, but it can't be 6.36. So it is a discrete variable. Also note that a binomial variable x always ranges from 0 to n in terms of its outcomes. Imagine I flip a coin 5 times, and coin flipping, by the way, is a classic example of a binomial process. If I define x to be the number of heads, I could get 0 heads, or 1, or 2, or 3, or 4, or 5 in that experiment. So the values of my variable x range from 0 to n. As I said a minute ago, P is the probability of a success, and 1 minus P is the probability of a failure. N and P are the two things that we need to know to actually calculate binomial probabilities. Now, we want to know how to calculate the f of x's, the probabilities. And we do it with the binomial probability function. Or I sometimes just call this the binomial formula. F of x is equal to n factorial over x factorial, n minus x factorial, p to the x, 1 minus p to the n minus x. Again, remember that f of x is the probability of x successes in n trials. N is the number of trials, and p is the probability of success on any one trial. And 1 minus p is therefore the probability of failure on any trial. Now, before we do examples, first I want to point some things out about the formula itself. There's actually two parts to this formula. The first part involving the factorials, which I'll talk about in a moment, and the second part, the p to the x, 1 minus p to the n minus x. In a sense, you've actually seen that part of the formula before, back in the module on probability. Remember that P is a probability of a success. 1 minus P is a probability of a failure. And notice you're multiplying probabilities together. Where did you multiply probabilities together back in the probability module? Well, you did it with intersections. This and this both, you were always multiplying probabilities together. And that's exactly what we're doing here. Suppose again, take an example. Suppose I flip a coin 5 times and I'm interested in the probability of 3 heads. Well, one way that could happen is I could get heads and heads and heads and tails and tails. And that's just a multiple intersection. You're going to have to take the probability of a heads times the probability of a heads times the probability of a heads times the probability of a tails times the probability of a tails. And that's exactly what these exponents are doing. We want x successes with probability p, and we want n minus x failures with probability 1 minus p. The second part of the formula is realizing that there's more than one way this event can occur. If you go back to my example of flipping a coin 5 times, if I'm interested in the probability of 3 heads, I don't care if the 3 heads come first, second, and third, followed by 2 tails, or first, second, and fourth, followed by 2 tails, and so forth. I need to count all the different ways this could occur. Well, that's where this part of the formula comes in. This is actually a combination formula. It'll give you the number of ways that you can get x successes in the n trials. Some books use the following notation for the combination formula. Some books will put it in brackets, nx. Some books will call it cnx for the number of combinations of x successes in n trials. But regardless of which of those notations you use, it's still calculated in the following way: n factorial over x factorial and minus x factorial. Now, some of you may have forgotten from your math background what a factorial is. So let's do a quick little review of factorials. Remember that n factorial is just n times n minus 1 times n minus 2 until you get down to the number 1. That is, you take n times every succeeding smaller integer until you get to the number 1. So for example, 5 factorial would be 5 times 4 times 3 times 2 times 1, which is already 120. 10 factorial would be 10 times 9 times 8, etc., till you get down to the number 1, and you would have 3,628,800. As you can see, factorials get very large very quickly. Also, don't forget that 0 factorial is equal to the number 1. It's not 0, it's equal to 1. Let's do a little work with the combination formula and with factorials, just again to jog your memory about factorials. Supposing I was interested in 7-4 here, that is, how many combinations or ways can I get 4 successes in 7 trials? Following the formula, that's 7 factorial over 4 factorial times 7 minus 4 factorial, which of course is 3 factorial. You can just do the subtraction. Now you might remember you can always do some canceling with factorials. The numerator 7 factorial is 7 times 6 times 5 times 4 factorial, 4, 3, 2, 1. But this way I can cancel this 4 factorial with the 4 factorial in the denominator. You'll be left with 7 times 6 times 5. 3 factorial in the denominator is 3 times 2 times 1, or 6. Now you can cancel that 6 with the 6 up here, and you're left with 7 times 5, or 35. Many of you will also have a factorial button on your calculators, and you can use that to help you find factorials. One more example. Suppose we want how many ways you can get 2 successes in 6 trials. That's 6 factorial over 2 factorial, 4 factorial. Let's get rid of the 4 factorial with the 4 factorial in the numerator, because the numerator is 6 times 5 times 4 factorial. 6 times 5 is 30, 2 factorial is 2, 30 over 2 is 15. So there are 15 ways of getting 2 successes in 6 trials. Some shortcuts that I usually like to point out. In doing the binomial formula, do you always have to calculate the combinations? Well, it's not a bad idea. If you forget these shortcuts, you can work it out. But if you remember these shortcuts, it might help. Anytime you have a 0 down here, that is, you want how many ways can you get 0 successes in n trials, the answer is going to be 1. If you think about it for a moment, how many ways can I get no successes? That means they all have to be failures, and there's only one way that could happen. If I'm flipping a coin 5 times, how many ways can I get no heads? There's only one way. You got all tails. Similarly, how many ways can I get n successes in n trials? That also turns out to be the number 1. How many ways can I get 5 heads in 5 flips? There's only one ordering that will do that. They're all heads. Lastly, how many ways can I get 1 success in n trials? This will always turn out to equal whatever n is. For example, how many ways could I get 1 head in 5 flips? There's going to be exactly 5 ways that can occur. The one head could come first with all the rest tails, or second with all the rest tails, and so forth. That is, it could be first, second, third, fourth, or fifth, so there'll be 5 ways to do that. Now let's get back to the binomial formula. And by the way, one of the reasons why the binomial formula is kind of important and used a lot in statistics is there's many situations where you have 2 outcomes of interest. Win or lose, vote for this candidate or not vote for this candidate, will this product be successful or not, and so forth. So there's many times when we can apply or use the binomial variable. I'm going to start with a simple little coin flipping example, and there's a reason why I'm going to use this one first, as you'll see in a minute. Suppose we flip a coin 3 times. Let x be the number of heads. Assuming a fair, well-balanced coin, the probability of a heads should be a half, and 1 minus p, the probability of a tails, should also be a half. Now here, since we're only flipping it 3 times, x, the number of heads, can range from 0 to 3. So I could get 0 heads, 1, 2, or 3. And I'm going to go ahead and work out the entire distribution using the binomial formula. Usually in most problems, we're not going to do the entire distribution, we'll just do a part of it. But there's something I want to point out on this particular problem. So here I've just repeated the binomial formula. Supposing we start with f of 0. What's the probability of getting 0 heads in 3 flips? Again, here's the combination part. 3 factorial over 0 factorial, 3 factorial. If you remember our shortcut though, this is just going to equal the number 1. 0.5 to the 0, we want no heads with probability 0.5, and if you remember your algebra, anything raised to the 0 power is the number 1. And then we'll have 1 minus p, 1 minus a half raised to the 3rd power. So this drops out of the formula, so does this. We're left with just a half cubed, or 0.125. So the probability of 0 heads is 0.125. Now I'd like to point something out. When p is a half, as it is in this problem, it turns out a binomial distribution is going to be perfectly symmetric. For example, in this problem, if you think about it, 0 heads, which we just calculated as having a probability of 0.125, 0 heads should have exactly the same probability as 0 tails. But 0 tails means you got 3 heads. Let's jump ahead for just a moment to f of 3, the probability of 3 heads. Again, here's the combination part, which is just going to equal the number 1, because there's only one way of getting 3 heads in 3 flips. A half cubed, a half to the 0, this drops out of the formula. Again, we're left with a half cubed, or 0.125. So notice f of 3 and f of 0 are the same probabilities. And as it turns out, f of 1 and f of 2 are going to be the same by symmetry. But let's go ahead and work them out. F of 1, the probability of 1 head in 3 flips, would be 3 factorial over 1 factorial, 2 factorial. A half to the first, a half to the second. You might remember from algebra, half to the first, half to the second, you can add the exponents together. That'll just be a half cubed. The combination formula here is equal to 3. Remember one of our shortcuts? How many ways can you get one head in 3 flips? There'll be exactly 3. So we have 3 times a half cubed, or 0.375, as the probability of one head in 3 flips. Finally, let's look at f of 2. Now here, none of our shortcuts really meet the criterion here for solving the combination part of the formula. 3 factorial over 2 factorial, 1 factorial. You can cancel the 2 factorial with part of the numerator. You'll be left with 3 divided by 1, or 3. There are 3 ways of getting 2 heads in 3 flips. A half squared again, a half to the first, again add the exponents together, and once again we have 3 times a half cubed, or 0.375. Here on the next slide I've written out the entire distribution that we just figured out. X, the number of heads, can be 0, 1, 2, or 3, with f of x's 0.125, 0.375, 0.375, and 0.125. Again, you can see that the distribution is perfectly symmetric, the same on both sides. That'll always be the case when p is a half in a binomial. It's not the case when p is not a half. However, we'll actually make use of that fact in a future module. Let's do one more example. Assume that 80% of college students own smartphones. In a random sample of 5 students, what's the probability that all 5 own smartphones, or that at least one owns a smartphone? Now here we're not going to work out the entire distribution, we're just going to solve parts of the distribution. Let's start with part A, all 5 owning smartphones. We define our variable x to be the number of people who own smartphones. We took a sample of n equal 5 students. You were told the probability of owning a smartphone was 80%, or 0.8. So in part A of the problem, we want the probability that x equals 5, or we can call that f of 5. Again, the combination formula we can use a shortcut on. There's only going to be one way of getting 0 students out of 5 who own smartphones. 0.8 to the 5th, and 1 minus 0.8 or 0.2 to the 0. Anything to the 0 is 1. That will drop out of the formula. So if you work this out, 1 times 0.8 to the 5th times 0.2 to the 0, that drops out. You're left with 0.8 to the 5th, which is 0.32768. Almost a 33% chance that all 5 students will own smartphones in this case. Let's look at part B. At least one owns a smartphone. Now you've got various ways to do this problem. You've got the hard way and the easier ways. And I'm sure you would rather do the easier ways. The hard way realized that at least one owning a smartphone would mean 1 or 2 or 3 or 4 or 5 of the college students. So you could use the binomial formula and calculate f of 1, f of 2, f of 3, f of 4, and f of 5, and add them all up. But that would involve doing 5 binomial calculations. The easier way to do part B is to do the complement. That is, at least one owning a smartphone has to be the complement of none owning a smartphone. Or as I write it down here, the probability that x is bigger than or equal to 1 excuse me, is equal to 1 minus the probability that x equals 0, or we can write that as 1 minus f of 0. I want 1 or more of the 5 students owning smartphones, but the only other option is none of them own smartphones. So I can simply calculate 1 minus f of 0, or 1 minus, here's how we do f of 0 with the binomial formula. Again, the combination formula is going to drop out. It's just going to equal 1. There's only one way of getting no successes in 5 trials. 0.8 to the 0 will drop out. That's equal to the number 1. And you're left with 0.2 to the 5th. So we're going to take 1 minus 0.2 to the 5th is 1 minus 0.00032, and we end up with 0.99968. Almost certainty that at least one of these students is going to own a smartphone. Better than a 99.9% chance that at least one will own a smartphone. Okay. And if you're not familiar with the binomial formula, you should certainly practice it. Now, for those of you with TI 83 or 84s, the binomial is programmed into your phone. By the way, even those of you with TI 83 or 84s, you should still know how to do binomial calculations by hand, just in case your calculator blows up or needs new batteries or something like that in the middle of a test. So you should be able to do them anyway. But to solve binomials on the TI 83 or 84, first press the second level button and then press the VARS button, which accesses the distribution list. Scroll down, and you'll eventually find two letters. On my calculator, they're A and B. They might be different on different models of calculators. One of them says binomial PDF and one says binomial CDF, or abbreviated that way. As it says here, binomial PDF, probability distribution function, is for solving exact values of the binomial variable. So if you want x equals 0 or x equals 1 or x equals 5, you will use the binomial PDF. Binomial CDF is a cumulative distribution function. You should remember from an earlier module what a cumulative is. A cumulative gives you, in this case, all probability less than or equal to a particular value of x. That can be useful then if you want all probability less than a point, or you can also in some cases do a complement, such as 1 minus everything above a point. But again, remember that the cumulative will give you everything less than or equal to a particular point. The format is to plug in n, p, and x. That's the three things once you access the binomial on your calculator. It needs to know n, the number of trials, p, the probability of success, and x, the number of successes. So for example, in our previous problem, where we took 5 students, we had an 80% chance of them owning a smartphone. Press your second level button, VARS, go to the binomial PDF. When you want to solve for f of 5, you'll type in n is 5, p is 0.8, x is 5, and again, separate these by commas and hit enter, and you should get the answer that we gave you earlier. For part B, the probability of x at least equal to 1 student owning a smartphone, let's find f of 0, and then we'll just subtract it from 1. So to get f of 0, again, you press the second level VARS buttons, scroll down to the binomial PDF, plug in 5, 0.80, and hit enter. That will give you f of 0, then you subtract it from 1. Okay, the last thing we want to talk about here in this module deals with the mean and variance and standard deviation of a binomial. Now remember, the binomial is a discrete variable, and earlier in the module you learned how to calculate expected values and variances. Recall this formula, E of x is summation x f of x, and we had a couple different formulas for variances. However, there's a much easier way to calculate the mean and variance of a binomial. These formulas that we had earlier, remember, would require that you knew the entire distribution. We'd have to have all the values of x, and we would have to have calculated all their probabilities. Fortunately, if we know a variable is binomial, we're going to have kind of a shortcut. First, let's start with the mean. The mean of a binomial, or its expected value, is just equal to n times p. If you think about it, this should be kind of intuitive or logical. Supposing I flip a coin 100 times, which is actually the example I have on the next slide that we'll get to. But suppose we flip a coin 100 times, and I define a variable x to be the number of heads, and I asked you, what's the average or expected number of heads? If you think about it for a second, you should come up with the answer 50. How did you come up with 50? You just took n of 100 times the probability of a head's a half. 100 times a half is 50. And that's exactly how you would find the mean of any binomial. Now, the other two formulas here won't be as intuitive, but they are provable in mathematics, but you don't have to worry about the proof. If x is a binomial variable, the variance of x, or sigma squared, is just n times p times 1 minus p. And if that's the variance, then here's the standard deviation, just the square root of that. So let's continue the problem I was just talking about. We flip a coin 100 times, and x is the number of heads. Coin flipping is a binomial process. On each trial, we have heads or tails. The probabilities remain the same on all trials. So we can just apply the formulas we just gave you. E of x, 100 times a half, or 50, as we said before. V of x would just be 100 times a half, or 25. And the standard deviation, take the square root of 25, and you'll get 5 would be the standard deviation. And that's all you need to do to find the mean, variance, and standard deviation of a binomial. And that's the end of Module 5. And now that we've discussed discrete variables in Module 5, we will go to continuous random variables in Module 6.